Hi everyone, I'm CHR Chuck presenting our CPP 21 paper towards formally verified compilation of tag-based policy enforcement. I want to start with the policy enforcement part by reviewing what a reference monitor is. Legacy software, especially when written in unsafe languages like C, C++, pose a large security challenge. One way to address this without modifying a legacy code base is to apply a reference monitor. Monitors prevent bad behavior in the system by terminating the system's normal execution or fail stopping, thereby enforcing a security policy. For example, monitors can enforce information flow control or IFC policies that make sure that secret data is never leaked from public channels, or a memory safety policy ensuring that all stores occur to valid memory locations, or a compartmentalization policy that reduces the attack surface of modules by making sure they were accessed only via their APIs. One way to monitor a language like C is to figure out where monitor check could happen, where a policy rule could be run. The diagram shows some possible places with the blue arrows. These are places where computations or things in the runtime happen. The rules operate on metadata tags that are attached to but separate from the C data. We also have a PC tag that tracks ambient program state, so named because it is updated through program execution, just like the PC. We see the signature of an add rule here. T1 and T2 are tags of the operands. TP is the PC tag that tracks program state. Rules either produce a fail stop, which enable policies to be enforced, or they propagate a new PC tag, here TP prime, and produce a tag for the result of the add, here TRES. Metadata tags can be defined arbitrarily. They might represent things like security levels in the IFC policy, or in the memory safety policy, whether or not a memory location has been allocated. Rules work only over tags. This makes the monitor easier to integrate with legacy systems. Monitoring is possible in software, but would be prohibitively expensive. So we could try a hardware solution. The pipe architecture extension implements a hardware-assisted reference monitor. It's a research project that is now becoming commercially available. In this diagram of a typical microprocessor design, it is represented by the green portions, which are tags on the regular components such as the PC, instruction store, register file, and memory. Tags are large, roughly the size of a pointer, so that they can point to or define arbitrary data structures in a protected memory. Pipe includes a TMU, or Tag Management Unit, which is the main mechanism providing the monitoring. The TMU runs over the tags, executing tag rules, which form the policy. The TMU has a similar data path to the ALU. When an instruction is run on registers or memory, an associated rule is run on the tags of those registers or memory. Now, the TMU also takes the instruction tag and the PC tag. Note, this means that the pipe rules run per instruction. Actually, the TMU acts like a cache and only has to run the tag rules on misses. Simulations show that when running a useful combination of policies, this can incur less than 10% overhead. To enforce high-level policies while taking advantage of pipe hardware, we can compile a high-level program and its policy to pipe a where target code and an equivalent policy. However, the compiler is now part of the TCB being those components that are critical to a system's security guarantees. So of course, it is now very useful to verify the compiler. Our effort to realize such technology has resulted in Tagine, our verified pipe-aware prototype compiler. Tagine has been heavily adapted from the ComCert verified C compiler. We studied two passes, one a translation, the other an optimization. The translation pass is based on ComCert's RTL-gen and its source and target intermediate representations, or IRs. The source of the translation pass is an imperative language with high-level notions such as expressions and structured control flow. The target is an instruction-based language. The optimization pass, based on ComCert's state code, is done over the instruction-based IR. The key point of Tagine is that it preserves fail-stop behavior. If a source program fail-stop, so does a compiled program. This is our notion of policy preservation. Our IRs have the standard program behaviors and additionally a fail-stop behavior. Due to the determinacy of our source and target, we can show that source and compiled programs always have the same behavior. However, we do restrict ourselves to programs that don't go wrong. This satisfies our notion of policy preservation. The preservation theorem is proved via the standard application of a forward simulation argument, whose format is shown in the commutating diagram, combined with the determinacy of the target. The most intricate and therefore interesting part of the simulation argument was the matching relation here. It describes what it means for a source program state to be similar to or to match a target program state. The simulation lemma essentially says that for every source computation, we can find an equivalent target computation. I enthusiastically refer you to our paper for fuller details. In order to remain as general as possible, we may want to remain policy independent, which is when the compiler knows nothing about the policy's rules. This has some benefits. Particularly, we can change policies without program recompilation, perhaps even while the program is running. With policy independence, policy preservation means that we have to find a way to invoke source rules in the target execution, and we must invoke them in the same order and with the same arguments. Note, this last bullet includes the PC tag argument to tag rules. So how can translation do this? In general, source constructs with a control point, with a single control point, are compiled to multiple instructions. Further, many different source constructs may use the same set of instructions. For example, an add may come from an expression or stack pointer arithmetic. And of course, mobs are compiled from many source constructs. Our paper shows how our compilation scheme, using instruction tags, addresses the first 2 points here. Our compiler defines a target policy by embedding source rules into target rules, and our verification shows that these are invoked in the same order as source. For the third bullet here, the regular preservation of the sequence of operations and the data they receive accounts for tag rules getting the same operand or value tags at both source and target levels. However, PC tag propagation has to be verified separately as there's no regular analog. Let's take a look at an example. Here we have an if-then-else. An IFC policy may want to capture the security context at the split point and restore it at the join point in order to prevent implicit flows while also preventing label creep. This required inserting pseudo instructions into target code that would save the PC to the register file. Preserving these registers and join points in general were a novel addition over the COMSIRT proof to the verification of Tajid. This required the most intricate and interesting clauses in the matching relation. Turning to optimizations, let's start with an example of how policy dependence blocks dead code elimination. In the left column here, the register RD is unused at the end of the function. Therefore, the add is dead and is a candidate for removal. However, in the pipe setting, if there's even a chance that the add rule might fail stop, we can't remove it because we have to preserve fail stops. And if we know nothing about the policy, there is a chance it could fail stop. Attempting to verify optimizations forced us to develop a framework of policy dependence to address these issues. Optimizations rely on analyses that tell us when code can be changed without changing program semantics. We need to be able to answer similar questions for rule semantics. For example, you need to understand when tag rules are dead in order to do pipe-aware dead code elimination. One way to do this is to characterize useful properties of rules that tell us just enough to enable sound optimizations. Mostly, we want these rules to be easy to decide, or at least statically approximable. They would also have to account for the PC tag if there's no analog for that in untagged code. A long presentation and paper contain many more details and answer many more of these types of questions. With that, I'd like to conclude by highlighting our major contributions, which include the design of a compilation scheme that preserves tag-based policies, the design of a framework for and analysis of the requirements of optimizations for tagged code, and realizing these designs in the prototype compiler. Also, check out our longer presentation and paper for interesting future work. Thank you. That's our talk.